Good morning, one and all. I welcome you all for this 1 week online short-term course that is being organized by Department of Chemistry in association with American Chemical Society and Viva Vigyan Bharati Faridabad. So I welcome you on behalf of JC Bose University of Science and Technology. So we are having fortunate to have with us Dr. Jawaharlal, Viva President Haryana. So I would like to request you, sir, to have some words on International Mother Language Day because we are going to celebrate the same also. Sir, may I request you to please?
Yes, yes. Thank you very much. Am I audible?
Yes, sir.
ठीक है। सबसे पहले तो सभी को सुप्रभात और जैसी बोस यूनिवर्सिटी ऑफ साइंस एंड टेक्नोलॉजी और विभा हरियाणा की तरफ से संयुक्त शॉर्ट टर्म कोर्स के लिए मैं आप सभी को बधाई देता हूं और सभी का आभार भी व्यक्त करता हूं कि सप्ताह में 2 दिन जो ये सेमिनार करवाया जा रहा है उसमें बहुत रेप्यूटेड इंस्टीट्यूशन से रिसोर्स पर्सन इनवाइट किए गए हैं और मुझे उम्मीद है कि सभी पार्टिसिपेंट्स जो है इसमें लाभान्वित हो रहे होंगे। आज अंतर्राष्ट्रीय मातृ दिवस है। मैं आप सभी को इस विशेष दिवस की बधाई देता हूं। मातृभाषा एक ऐसी हमारी भाषा है जो हमारे मन के विचारों को, मन के भावों को बहुत ही सरल तरीके से समझा सकती है। गांधी जी ने कहा था कि अगर कोई भाषा पूरे देश को एक सूत्र में पिरो सकती है तो वो हमारी मातृभाषा है। इसलिए हिंदी भाषा है, मातृभाषा जो है वो चुना गया, इसको स्वीकारा गया। इसी प्रकार अभी आपने देखा है कि 2020 में जो नई शिक्षा प्रणाली आई है उसमें इस बात पर विशेष जोर दिया गया है कि किसी भी बच्चे को पहली से 5वीं कक्षा तक उसको मातृभाषा में ही पढ़ाना चाहिए। तो मातृभाषा हमें इस हर विचार को अंतरंग भाव से समझने में हेल्प करती है, सहायता करती है, क्योंकि जो बच्चा सबसे पहले भाषा समझता है वो माँ की भाषा समझता है। विज्ञान भारती पर स्वदेशी विज्ञान आंदोलन में और विद्यार्थी विज्ञान मंचन के साथ सभी तरह से कार्य करती है। मैं आप सभी को इस दिवस विशेष की बधाई देता हूं और जेसी बोस यूनिवर्सिटी और साइंस एंड टेक्नोलॉजी का भी आभार व्यक्त करता हूं कि जिन्होंने विभा हरियाणा के साथ मिलकर के ये कार्यक्रम किया है। ये जी जो हमारे विभा हरियाणा की जॉइंट सेक्रेटरी भी है और इस कार्यक्रम की कोऑर्डिनेटर भी है, उनको और पूरी टीम को मैं बधाई। धन्यवाद।
So thank you very much, sir. We are very fortunate to have you with us. So now I welcome you all for this day 4 session 1. So in this session 1, we are going to have a talk uh, from Dr. Anurag Gaur. So Dr. Anurag Gaur is going to talk with us on fabrication of energy conservation and storage devices and approach towards Aatmanirbhar Bharat. So as far as brief introduction for Dr. Anurag Gaur is concerned, so Dr. Anurag Gaur received his PhD degree from IIT Roorkee in 2007, and presently he is working as assistant professor in Department of Physics, NIT Kurukshetra. So Dr. Gaur has research work on functional nanomaterials for energy storage devices and spintronics. So Dr. Gaur has published around 120 research papers in reputed research journals in India as well as in abroad. So Dr. Gaur has handled a number of research projects funded by various government schemes. So Dr. Anurag Gaur has been awarded Young Scientist Research Projects Award by Departments of Science and Technology, Government of India. And as far as research supervision is concerned, so he has supervised around 7 PhD students and around 50 MTech theses. So Dr. Gaur is also an editor of Applied Science Letter and reviewer of various national and international journals. So that includes AIP, Elsevier, IOP, Springer, etc. So Dr. Gaur is also life member of Material Research Society of India and American Chemical Society. So he has delivered a number of invited talks in India as well as in abroad on various topics. So now I would like to request to Dr. Anurag Gaur to please start the talk. So Dr. Anurag Gaur, sir.
Thank you very much for this introduction. और सभी को मेरा नमस्कार. Good morning to all the participants as well as the respected faculty members who joined this conference or this session. And also the thanks to Dr. Jawar Lal sir, President Viva Haryana, that who is with us for this session. And Bindu ma'am, that she is always very active and organize very good events. So today in this talk, I will just firstly share my screen. I will speak on this topic of so my screen is visible, please confirm.
Yes, sir. We got the same.
Okay. So I will speak on the topic of this fabrication of energy conversion and storage devices.
Gaur sir, if possible, please, we want to have it in full screen mode.
Okay, I do.
If possible.
Okay, no problem. So now this is okay?
Fine.
Okay. So I will speak on this fabrication of energy conversion and storage devices. And the approach towards Aatmanirbhar Bharat is that this is the mission of our Prime Minister Shri Narendra Modi ji, that we have to be develop the products at our country, and for that there is a big role of the scientific community, that we have to be plan our research in such a way that we can do the research in terms of the demand of our society, that what are our problems, what are the requirement for our society. So that things we have to be addressed, and accordingly we have to plan our research, because now this is the time not only just to have the research only to limit it for the publications, we must come up with some product. So this is the new lines and this is a new direction is there for the researchers given by the Prime Minister of Shri Narendra Modi ji. So in this presentation, I will discuss some of the devices that we have fabricated in our lab. And so therefore, I will start with this, that you see that we have the top, if we consider that what are the top 5 problems for the coming 100 years for the humanity. So among that, these are, first one is the energy. Of course, you know that what is the importance of the energy for the economy of any country. So it's a very important, because for running all industries, machineries, or whatever, you want some energy. So energy is a very important topic, and its need is increasing continuously. Second, the water. So second is the water. So water is that, that without water, no one can survive. So that is also, especially the pure water, drinking water. It's also maybe that lot of work is required so that we can have this water in abundance for the coming generations. Food itself, it's a problem that has to be addressed for the humanity. Environment, it's also very important concern. that because of some enhanced industrializations, there are some very serious environmental concerns. So therefore, we also have to be work in that directions, and this is the poverty. So these are the 5 major problems for the humanity for coming years. But my talk is basically that I will address the first, a very small part of this first problem of the energy, that how we can become self-reliant and what kind of the things we can do about the energy sector. So first thing is that this is the energy production and generation. So you know that there are the different sources of the energy, but nowadays people are shifting towards the renewable sources of the energy rather than to these the gasoline based or the hydrocarbon based, these petrol, diesels, or some other the conventional source of the energy, because they pollute the environment. So therefore, we have to be shift toward the renewable sources of energy, and among them, you know that solar energy is very, very popular, and it's very much now is in use, that you can have the solar panels in most of the places and playing a very important percentage in the energy sector. There are also some other sectors for the renewable energy, either it is wind energy. Nowadays, you also know that people are shifting to the other sides. So I will just touch here one of the a very new approach for the electricity generation through the water splitting. So if we can do the water splitting by the materials, so that is the, because the short-term course, it is the advanced material. So we will discuss some of the materials they can use it for the electricity generation through the water splitting process. So in water splitting, what actually being done, that this water is being split into the hydronium ion as well as to the hydroxide ion. 2H2 is equal to OH minus ion, and this is H3O plus ion. So there are the different ways to split the water. Some of the people use the light is being used for the photocatalytic activities for splitting the water. But in this approach, that is, I am going to tell you that we are not using any photons, any light. So only material itself will split the water into the OH minus ion and hydronium ions. So this is the, because of some materials, they have the high affinity towards the hydroxide ions. So because of that, they will attract to the hydroxide ion towards one side, and then the hydronium ion towards the another sides. So because of that, within the material itself, so there is some electric field is developed within, because positive on the one side and negative on the one sides, because of the different affinity of the molecules which present in the compounds towards the OH minus ions. So under this influence of this electric field, the splitting rate of the water is further accelerated, it further enhanced. So because of that, water split in this OH minus ion and H3O plus ion. So then what we have with this material, this is our material side. And along with this, you can see that one side we use here the zinc electrode. And the other side we have the, this is, we are having these, the silver electrode, or either you could say that we have make the finger types of the silver contact. So it's like a cell, it's like a complete device. So it have the 2 electrodes, you can say, that is one side that we have the zinc, another side we have the silver. And in between, we will put this, our material. What is material? It is basically the magnesium ferrite. So you know that already the ferrite materials are very active, because the iron that is present in the different valency state in these compounds. So that's why these manganese ferrites, and particularly we have done doping in this material by the lithium. So that also further enhanced to accelerate the water splitting process, as well as it increased the sensitivity of the water dissociation by using this compound. So this magnesium and magnesium ferrite we have doped with the lithium. So there is also one of the reason to dope the lithium, that we are replacing this magnesium by the lithium. So magnesium valency, you know, it is +2 and lithium is +1. So because of that, some oxygen vacancies are created within the material. So these oxygen vacancy itself also, they can play the role to further improving and sensitizing the water dissociation property of this material, because the material property is that how we can split the water more and more into the hydronium and hydroxide ions. So, and this material, they are porous in nature, because you know that what we will do, we will put the water inside this material. So this water then it being absorbed within the pores of the material already present in these compounds. So we have to synthesize this material in such a way that it must have the porosity, because you know that in the material science, the important part is the synthesis. If you are a good material scientist, so then you must have the idea that how you can tailor the property of material just only to changing their morphology, just changing by their topography. So that is the thing. The material is same, their structure is same. It is the magnesium ferrite. So its structure is the spinal based structure. But what we are doing, we are changing their morphology, we are changing their topography, we are changing the grain size, we are increasing their porosity, we are improving their surface area. So that kind of the things you can do it in the materials, and you will find that there are a lot of materials, their properties are drastically changed once you change their morphology. So the same things we are doing in this material, we are making this porous, because porosity is very important. If water is not being absorbed in these materials, so you know that without absorbing, this reaction will, the water splitting property, water dissociation will not take place, and you will not get any current. So what is there? This is the mechanism. I just tell you about this, how this this works. So I just tell you about this, that how this works. So it is basically that we have this the magnesium, lithium doped magnesium ferrite material, and on this one side we have the zinc, and another side we are making these the silver contact. So silver contact we are making on the other sides. So what is the mechanism for this? That firstly, this lithium substituted magnesium ferrite material, it will split the water 2H2O into the OH minus ion plus H3O hydronium ion. Then what happen? These OH minus ions, they will move towards the zinc electrode. They will move towards the zinc electrode and they form the zinc hydroxide. So the oxidation reaction take place at this electrode, and during this oxidation reaction, the electrons will be emit. I'm sorry that the electrons are not being written. 2 electrons will emit by this oxidation reaction at this oxidation process. So these, and then these 2 electrons, they are emit through this oxidation process. They will just move outside the circuit, not inside. From the outside, they will come to the other electrode side, means toward the silver. And on the silver, you know that hydronium ion, they will move towards the silver electrode. They will collect it over the silver electrode. So these 2 electrons, they are coming outside from the circuit. They will come to the silver electrode side, and then reduction take place. Reduction take place at this electrode, and this, because of the reduction, then there will be flow of the charge. There will be the flow of the charge carrier from one side to another side, and that is the reason for the electricity generation in these materials. And the total cell voltage, that is, this is oxidation potential is 0.76 volt, and this is the reduction potential is 0.22 volt. So the total cell voltage of this this cell, this is 0.98 volt. So this is basically the mechanism of the working of this cell, which is used for splitting the water. So we called it it is a hydroelectric cells, because we are using here the purely water to split into the hydronium and these hydroxide ion, and then they are being moved towards the zinc and silver electrode sides, and the reduction, oxidation reductions take place, and that is the reason for the electricity generation in these materials. So this is the important, what is there for this work. You could say that what is the importance is, this work is that we are not using any extra source of energy. You know that in most of the device, you need some energy required at any level. Either you are battery, so you have to charge it. So for the charging, you again need some power from some other source. Or either you are using some supercapacitor, or either using some solar energy as well. So once you may have to store that energy, so then you need some storage also. But here you don't need any source of the power internally except the water. And even for the charging the cell, you again put the water. So no charging is required by using any source of the power. I just show you that some of the hydroelectric cells that we have developed in our lab. So these are some of the cells we have been developed. So these are in different diameter and in shapes. So we have made this magnesium lithium ferrite oxide based the hydroelectric cells. The diameter, this is the 1 inch diameter we have been fabricated. So the short circuit current for this cell it is 9.79 milliampere, and open circuit voltage is 960 millivolt. So the total output power, that is 7.68 this is milliwatt. And this, you see the diameter of this 2-inch cell. This is 1 inch, this is 2-inch cell. So that is 78 milliampere short circuit current we are getting through the water splitting. And the open circuit voltage is 920 millivolt. So the power output, this is 71.76 milliwatt. So that is a very good, that this much amount of power we are using. So that much power is not very huge, that it's not for the big energy requirements, but the small types of the energy applications, like for the lighting purpose, like for the these mobile charging and all that, we can utilize this the energy that are being produced, the electricity that are being produced by these hydroelectric cells only simply through the water splitting. So different type of the cells we have been fabricated, and to check their practical application, to check their demonstration, we have been tested that, and also we have been light up the different LEDs. So these are LEDs we have been light up by these hydroelectric cells. The bigger kind of this, again, this is the LED lamp that we have been light up. So what is basically the target of this research work, that what we want? So this is basically for the remote areas. We are working on to make a battery that will call the Pani ki battery. It will run by the simply on the water, and it is for those places where there is no power connection at all. Because even though if we are using the solar energy, so solar energy, it have some the investment is more, means you not only just have to purchase the panel, and panel cost will be, again, you know that in the at least 10,000 to 30,000, and then you need the storage, because solar energy, this is not it is intermittent in nature, it's only available in the daytime. So for the utilization into the night or some other times where in those days where sun is not available, so you cannot you have to store the energy. For the storing, again you have to purchase the battery. So then the cost increases. So that will take so that is not affordable for all the people to the remote areas. They are very poor. But if we can make this only the water is available everywhere, and even though there is no need that we need only the pure water, any kind of the water, tap water, we can use it. It will also produce the electricity. So we can make there at least the for the lighting purpose, we can make these cells, and the cost of a single cell, it will, with the LED and all that, the battery, that will be around 100 rupees. So within 100 rupees, we can make the cell, and that cell could be used for the lighting in the houses. We will use the LEDs there, and we can light up these LEDs. And the beauty is that we are not applying any, means for the charging, you don't need any source of the power. So what is there? You will put few drops of the water, it will light up. And once again, you have to put some drop of the water, so then it will be charged. So actually what is there? There will be a continuous flow of the water in the drops forms. So very small amount of the water is required. You don't think you required a very huge amount of the water. You can understand that only 10 to 50 ml, only 25 ml water is enough to light a single battery for the whole night. Only 25 ml. So that is a very small amount of the water is required to light up this. And the cost is very low. We are working on that to bring it into the final product form, that how this kind of the cells, they can be utilized for the remote areas where the people cannot afford even the solar panels, that and the other things for the lighting applications. So by these, because amount of the power is not very large, we are working on that to improve it, but that simply used for the lighting purpose by using the LEDs. So that kind of the hydroelectric cells and this kind of the work, it can be importance and have the energy applications for some other aspects, that how we can take up and how we can work on these cells for the lighting applications. And so that will be a very simpler, and it is very useful for the remote areas. Now we come to the second part of this presentation. You see that you see that the second thing is the major agricultural, because you know that our country, this is the agricultural based lot of economy, and the agriculture is that is the this is the profession of the many people of this country. So for that, it is a very important that how we can utilize the agricultural waste material, because this farming based economy of the country produce the huge amount of the agricultural waste every year in our country. So you could say that particularly into the Haryana and this western UP part, there are the major agricultural waste materials are like this is the rice straw and rice husk, and another is the sugarcane bagasse. So these are the two major agricultural waste in our region. The rice straw, this is, you know, it is a rice byproduct. It is produced after when the paddy is harvesting. So rice husk, that is one of the byproduct obtained during the milling of the rice. And this is the main agricultural residue obtained after outer covering of the rice is being removed during the milling process. Then we got this. This is the husk, and this is the, you could say that this is the rice stem that is being left after removing the rice from this. So this is the major agricultural waste in our region. Another is the sugarcane bagasse. This is one of the another major byproduct. It is obtained during the milling of the sugarcane. We extract the juice from it, and the remaining part, this is the bagasse. So these are the major sugarcane, these agricultural waste are available in our regions. But what actually the farmers do, because farmers, they don't have they don't if they don't see their the utilization of this waste material, so what they do, they generally burn these crop residue into the open air. So because of that, it leads to the air pollution. You have seen that there are a lot of problems, particularly in the month of this November, December. Once this, because in the winter season that already this humidity is high, and because of this burning of this crop residue, then there will be some hazy environment, and it create a lot of problems, health problems. So that is because of the burning of the crop residue, and it leads to the air pollution. So this air pollution released due to the this burning of these the crop residue, it produces some greenhouse gases, methane, nitrous oxide, carbon dioxide, and some other toxic gases, NH3, NOx gases, carbon monoxide, SOx. So these are very dangerous for the health. And even you see that there are some small particles, PM 2.5, means these are the particulate matter. 2.5 means 2.5 micron size. So they are very, very dangerous because they directly enter into our lungs through the inhalation process. So therefore, these small particles, they are they are PM 2.5, PM 10. So they are very dangerous for our health. So adverse health impact comes in terms of the asthma and other respiratory illnesses. So that, and this also the burning of these crop residue, it also contribute for the global warming. So, and there are adverse impact on soil quality as well. So there are a lot of problems. So therefore, that is thing that we have to address, that how the burning of these crop residue can be stopped, but stop only once we will give some amount to the farmers. We will purchase these byproduct or these the waste material, and we convert them into for some wealth, for some product. So then only this problem can be addressed. So for that, you see that this need of utilization of this agricultural waste material, this is very important, and the rapid depletion of the non-renewable energy sources, that also that we can work on that. And this agriculture waste is one of the member of the biomass, which is the attractive renewable energy resource, because you know in the renewable sources there is also nowadays the contribution of biomass is increasing. So this agriculture waste is also the part of the biomass. It will be the biomass this biomass will be utilized for the this energy production or conversion, and it is widely dispersed that it could not contribute the this zero net carbon dioxide emission to the atmosphere. So that is also the thing, because this is renewable in that sense, because crops that comes every year. So because of that, it contribute zero net carbon dioxide emission to the atmosphere. So this biomass has to be utilized as a raw materials, and this is for the pyrolysis to generate the liquid, gaseous and solid fuels. So, and this all waste material, the complete waste material can be utilized. It will come in forms of the liquid. Then you can say that these are the biodiesel can be forms in gaseous forms. So there are some gases they will be used to run the many systems, that it is also a very good source of the energy, and solid fuels that is also have some applications. So this pyrolysis process that reduce the gas vapor and then collect the liquid and solid char material from that. So basically from these materials what we have done, we have get there from the char materials. After pyrolysis of this material, we can collect some solid material, that is the solid char, and it is, you know, that it's a carbon based material, and then this solid char that can be utilized for activation carbon production. By using some chemicals we activate it and we bring it into the carbon activated carbon form, and then it will be utilized for in the battery and these supercapacitor materials. Another, the oil we got it, this oil, once this gas is being passed through the condenser, so it is being condensed and then it comes in some oil form, that is the bio oil, that is also being derived, used for some petroleum grade refined fuels. And this bio oil has several environmental.
तेरे बंद करो हाँ और तेने कह रही है नहीं, मैंने कही बाहर का ताला बंद करिए, ये तो बंद नहीं करी तेने, सीधा मैं जा रही हूँ.
Okay, so this the bio oil that has the several environmental advantage over the fossil fuels, because this is a clean fuel. So it is that CO2 and no SOx emission are generated because of this biomass material, and the biofuels that generate more than 50% lower NOx emission than as compared to the diesel oils in gas turbines. So therefore this the pyrolysis of this waste material, it has the high concentration of these carbon based materials, and that could be utilized for some applications. And if we see about these rice husk or rice straw, so they are, you know, that Asia generates over 90% of the world rice production. So together China and India accounted for half of the world rice supply from these two countries. Paddy, you know that it's an average consists of 72% of rice and 5 to 8% of grain, and the 2 to 20% of the husk. So it is estimated that every ton of the paddy that produce about 0.20 tons of the husk. So it's a huge in amount. So the partially burnt rice husk that in turns to the environmental pollution. So it would be beneficiary to the environment if we could recycle this waste material for some eco-friendly materials and to generate a high end value product. If we see the chemical analysis of these materials, so rice straw and rice husk, this is material. So basically it has the cellulose, lignin and hemicellulose. So you know that they are carbon rich material. So they have 74% cellulose, lignin and hemicellulose. SiO2 is 15 to 22% and some 4% some other constituents. So they are carbon rich materials. Similarly, the sugarcane bagasse, it is also that India is one of the largest country that produce the sugar in the world, and only industry absorb 10% of this bagasse production. So remaining 90% is unutilized. It is either burnt or some that kind of purpose which pollute to the environment. So 1 ton of the refined sugar result 2 tons of the bagasse. You could see that how much is the wastage or how much is the bagasse is produced. So this is because of this sugarcane is one of the most promising agricultural source of biomass energy in the world, because in some other countries, because of high energy to volume ratio of this sugarcane, so that is being used as the nature most effective storage device. So for that, the sugarcane bagasse, it's the if we see their composition, it contains cellulose, lignin and hemicellulose around 83 to 96%, while the S's are 1 to 4%. So that is the reason we have to utilize these sugarcane waste materials, and therefore you see that we have been utilized this sugarcane, this agricultural waste material for some energy applications. So what we do that we suppose we have taken this for the sugarcane bagasse material. So firstly, we convert this into the porous carbon. So there are some procedure. By using that procedure, we convert this sugarcane into the porous carbon materials. So what do that? It's some physical activation. Then we do some chemical activation. So via that process, we will bring it into the porous carbon, because porosity is important for any material you want to use it as an electrode into the energy storage device. Either it is batteries or either these are the supercapacitors. So you need some porous material, because the porosity is required so that the electrolyte ion, they could enter in the pores, they could intercalate into the pores and could remain, could spend some time in these pores, and then they come out for some other oxidation reduction reactions. So material should be porous in nature, and it should have the high surface area that is always required for these energy storage devices, electrode materials. So we made it a porous carbon. So firstly we make material, and this porous carbon material, then we have make it the slurry. Slurry is being added, that you have this powder material, you can some black carbon, then you also can add up some 80% your this activated carbon, 10% carbon black, and 10% PVA, and you make this slurry. Then this slurry has to be coated over some current collector. It may be the nickel foil or some graphite sheet, and you do the coating of this material. And the coating, you can then this make bring it cut in these the shape of the coin cell, because our purpose is that we want to fabricate the coin cell. So that kind of electrode has to be cutted because of the cutting machine and punching machine. And finally, once you do that, we can assemble the full device. So full device means, my meaning of full device is that we have two electrodes, in between there is some electrolyte. So then you can assemble this. So we make the two electrodes separately and then put it some separator in between, and then you can punch it, and you can get this fabricated cell. So in this cell, we have used one electrode of this carbon based material, another is the metal oxide, and by that we have been fabricated. So that can be used for some energy application. So that is the utilization of this waste material. So we can utilize these agricultural waste material as well for some energy application.
All the audiences, please make sure your microphones are off. Please mute them. Anyone who is controlling the meeting, please mute all. Thank you. Sir, you please start.
Okay. So the results that we have been for this carbon electrode material that is fabricated from the waste material, and this cell, the specific energy we have been calculated, it is 6 watt-hour per kilogram. So that is good for utilizing these waste materials. So that was the one of the purpose of that how we can utilize our waste material for creating to some product or some to make the energy generation. Another thing is that now we have to become up some the energy storage devices. That is the third part. As you know that in the current time there is a huge demand of the energy storage devices. Nowadays the people that hybrid vehicle concept is coming. Government, every country government want that there should be most of the electric vehicle on the road rather than to these hydrocarbon based, diesel and petroleum based electric vehicles. So there is a huge demand of energy storage devices, these batteries, supercapacitors, because not only for the hybrid vehicle, already in the solar energy you need the battery, and not only the solar energy, any portable device you have, it wants some energy storage, because any device, it needs some energy for their functioning. And if you are making it portable, it must have the battery, either your mobile phone, either your cameras, so whatsoever. So there is a huge importance of the energy storage devices. And if we look that there are two major energy storage device, one is the batteries and another are the capacitors, supercapacitors. So battery, I just firstly I will touch some of the fundamental part, that what is difference in the battery and supercapacitors, how they work, and then I will show you that some of the materials they are being used to fabricate the supercapacitor materials with some very high performance. So then firstly, you just see that how the these batteries and capacitors works. So battery, they works on they convert chemical energy into the electrical energy. So means you know that the like lithium ion battery, so there are some oxidation reduction reactions take place, and because of that is the region of the charge storage in the battery. While in capacitors, I'm talking about the conventional capacitors, they store the charge electrostatically, means no chemical reaction take place, only the charge carriers moves towards the electrode side once you charge the capacitor under the influence of electric field. So the charge carriers only just move from one side to another side under the influence of the electric field, but they are not playing role for any chemical reaction. So that is the working of the capacitors. And the capacitor capacitance, you know that it can be C is equal to epsilon A upon D, where the if you want to increase the capacitance, then what you have to do? You have to increase the dielectric constant of a material for the conventional capacitor, and then area, this is the area of your electrode, it must be large, and D, this is the distance between the electrodes or plates, it should be minimum. Then you can increase the capacitance, because if you want to increase the energy storage capacity of a device, storage device, so their capacitance should be high, because you know that the stored energy is equal to half CV square. So then the C should be large, capacitance should be large, as well as the cell voltage should be high. Then there will be, it can store the high energy. So we have to be work out that in capacitors, so supercapacitor are what? They have the high capacitance. So their capacitance is too high, they will call the supercapacitors. And how they works, and if we see that what are the difference between battery and supercapacitors. So battery, they have high energy density, while the capacitors, they have the high power density. So you may understand that energy density means that if you want to utilize the stored energy for the longer duration, it should be released in a small amount. So then the energy density high must be required. And if you want that the instantly all the stored energy should be released, then it means that you need the high power density is required. So in batteries, generally high energy density they have, so that the battery, you know, they can be discharged in a long time. But capacitors, they will be immediately discharged. So that is the, you could say, the drawback in that sense. However, charging is fast for capacitors and it is long for the batteries. But discharging time is very less for capacitor, and it is good for the batteries, because the battery have the high energy density. Second thing is battery, they have the limited cycle life. You know that everyone use the batteries in mobiles and all that. So it has the life cycle, your lifetime. After 2 years, 3 years, your battery, either this performance goes down, or either it's not working, functioning properly, because you know that chemical reactions take place in the batteries. And because of there are some number of cycles, only up to that it could run efficiently. After that, the structure of your material may be collapsed because chemical reactions are there, and then the performance of your battery goes down. But in capacitor, they have the long cycle life. Reason is because they are not having any chemical reaction, only there are physical movement of the charge carriers. So because of that, their cycle life is very, very high. And if we see about the charging time for the battery, it's low. They took the long charging time. It may take few minutes to the hour to charge up the battery, but capacitors, they are very short charging time. In few seconds, they can be charged. Another thing is battery, they have voltage and current limitations, while the capacitors, they have the high load currents. Battery, they have high temperature sensitive, while the capacitors, they have excellent temperature performance. So capacitors have the good things, but only thing is that they don't have the high energy density. So that is required, that how we can improve the energy density of the capacitors. So for that, we can see that the solution is supercapacitors. Supercapacitor means, as the name itself indicating, supercapacitor means their capacitance is super, very high. So they will call the supercapacitors. So we have seen that capacitors, normal capacitors, their power density is very high, but energy density is very low. While in the batteries, the energy density is high, and the power density is low. So there is a huge gap in the capacitor and battery, and this gap is being fulfilled by these electrochemical capacitors, or either you could say them the supercapacitors. So this supercapacitor, how this works, we will have a look on that. The C is equal to epsilon A upon D. This is the capacitance I told you for a conventional capacitor. So to enhance the capacitor, A should be large. So that is the first thing, we have to make those kind of material which will have the large surface area. So we have to do this thing during the synthesis of material. We adopt those method of synthesis that these materials should have the large surface area and D should be smaller. So in case of the supercapacitor D, this is the order of angstrom, 0.3 to 0.8 nanometer. So naturally the capacitance is high for these supercapacitors. While this is very smaller, I will tell you ahead. So supercapacitors, they are basically two types: electric double layer capacitors and pseudo capacitors. So electric double layer capacitors, they are like a conventional capacitor, and there the charge storage is through the this is electrostatic. So by the electrostatic process, we have the charge storage in that. While pseudo capacitors, they are basically pseudo capacitor means they store the charge electrochemically, even combined effect also, that EDLC as well as the electrochemical. So generally the carbon based materials, either activated carbon, either carbon aerogels, carbon nanotubes, graphene, or other carbon based compounds, they show the EDLC effect, while the metal oxides and these conducting polymers, they have the pseudo capacitance behavior. So this is the things and difference between these two capacitors. And nowadays the time is for the hybrid capacitor, because we want that there should be the significant value of the energy density as well as to the power density. So what we do, we will have some, this is the carbon based material, and some of them is we can have the battery type material. So we mix up one electrode, you can take battery type, another electrode you can take the this EDLC type. So by using both of these two, we can make the hybrid capacitors. So these hybrid capacitors are very important and are being used nowadays for this purpose. How the capacitor work, and particularly the EDLC capacitor, just I very fastly I tell you with this. So we can see that in EDLC, electric double layer capacitor materials, how they works. So you know that I already told you that our electrode must be porous in nature. This is the electrolyte. So once I apply the voltage for the charging of the capacitor, then what happens? Suppose this is positive terminal. So negative charge carrier, they will come to this side and positive to this other side. So at this interface of our electrode material, there will be the charge is pile up, this positive this way and negative this way. So because of that, it itself working as a single capacitor, and the distance between these two is at angstrom level, I told you. So because of that, the capacitance is too high, and this another capacitor will develop to this other electrode side. So because of that, we want some separator so that the short circuiting could be avoided. And this separator is porous in nature, so that electrolyte ion, they could be crossed from one side to another side. So this is the region, it is called double layer capacitor, because there are two layers are formed, and the distance between these, this single one, this is of angstrom level. So because of that, the capacitance is very, very large. It is of the order of 0.3 to 0.8 nanometer. So that is very important to be understood at this point, that there is no transfer of charge between electrode and electrolyte here, because charge mechanism in these materials, in these supercapacitors, is basically purely electrostatic. So no chemical reaction is here. But if we go to the other types of the material supercapacitors, they can have the chemical charge storage, because there are some reversible Faraday redox reactions take place. And you see that there is a charge originate because of the consequence of these reversible redox reactions, intercalation process. So this phenomena is observed in metal oxide materials. So that is the reason metal oxide based pseudocapacitors, their capacitance is roughly 100 times higher than to the EDLC based supercapacitors. So naturally their capacitance is high for the pseudocapacitance based, because they are based upon the redox reactions like the batteries. However, EDLC, they have the high power density, their energy density is less. So that is the reason that the solution of this is we have to work. This is the some parameters of supercapacitors and batteries that we have. So this is the charging time for supercapacitor is, you know, that very fast. For battery take time, it is 1 to 10 seconds only for supercapacitor, but for the lithium ion battery it is 10 to 60 minutes. Cycle life, this is 1 million for supercapacitor, while for the battery only 500. Cell voltage, so you see that only thing is that the specific energy, the energy density is very, very less for supercapacitors. It is only 5 watt-hour per kilogram, while for the battery it is 120 to 240 watt-hour per kilogram. So part we have to be improved for the supercapacitors. Power density is already very high for them as compared to the batteries. So energy density we have to be improved. And for that, the solution, this is basically the hybrid materials applications of supercapacitors. You know, there are many modes. They are used in hybrid vehicles, in all the portable devices. Buses are running by the supercapacitors. So there are a lot of applications for that. This is the bus that being run in some countries for the city purpose, and there will be some pantograph types that we have in our railway system. So at every bus stop, it got charged. So and you know that supercapacitor take very few seconds for charging. So during the time of the passenger get down and enter, this being charged at every station. And but thing is that it cannot run for the longer distances. For that, you only have to then see that how. So this is how these supercapacitor are installed in a bus. You know that for the solar energy, again you need some energy storage. Battery must be required. So for that, even for the wind energy, you require some this energy materials. So basically, the thing is that in difference between the battery, pseudocapacitor, and EDLC, that battery material, they are non-capacitive Faradic storage, EDLC non-Faradic capacitive storage, and while pseudocapacitor, that has the combined effect of these two. You can also see through the CV curve that why these are the different materials. If you are having this kind of the CV, this is rectangular shape, and is EDLC, and if it is like that, oxidation reduction peaks are clearly observed. So this is like the battery materials, and this is the pseudocapacitor. This is the combined effect of these two. Similarly, for the GCD curves, you also can realize it is curve, while this is peaks will forms in battery materials, and while for the pseudocapacitor it is non-linear. So by the GCD curve and CV curve, you can identify either your material EDLC, either type, or either it is the pseudocapacitors. So these are some methods that how you can calculate the capacitance, energy density, power density. So concern is that we have to be come up for the hybrid materials. Hybrid materials means that what kind of the materials we can make it. So hybrid means that either we can make the composite, or either we can do the approach. We can select one of the electrode of battery type and another electrode of the, this is the pseudocapacitor, this is EDLC type. So by that way, we can have the high energy density as well as the power density. So can I know that how much time I have for this presentation?
So, sir, you have 25 more minutes in case you want
25 more. Okay. So now just I just come up some of the work now, that how these supercapacitors are formed. So you can see that how the supercapacitors are formed. So for that, we have first of the work that I'm showing to you, that we have made the graphitic carbon nitride ZnCO2 hybrid electrode materials that is based upon, and it's a symmetric supercapacitor. Symmetric means, what is meaning of symmetric supercapacitor and asymmetric? Symmetric supercapacitor means if the both electrode of your supercapacitor are of same material, so that is symmetric. And if they are of one electrode is some other material, second electrode is some other material, so that will call the asymmetric supercapacitor. And using gel electrolyte. So we are using here the gel electrolyte. Gel electrolyte, why we are using that? Generally people use the aqueous electrolyte, KOH, NOH. One thing is that the dissociation voltage is less for the aqueous electrolyte and it is high for the gel electrolyte or some other organic electrolytes. So second thing is that if you use the gel electrolyte, then in the aqueous electrolyte, there is a problem of the packaging. There is the problem of the leakage take place. So but if we use the gel electrolyte, so that kind of the leakaging problems can be avoided, and they are flexible in nature as well. So firstly, what we do, you see that, and how we are making this composite. We have taken one material is graphitic carbon nitride, another is zinc cobalt oxide. So I told you in the starting that one is the carbon based material, it will have the EDLC effect. Another is the zinc carbon cobalt oxide, it is a metal oxide, so it will have the pseudocapacitor. So we are using the composites we are making, means the supercapacitor is symmetric, both electrode are of same material, but even a single electrode is not of the same material, it is a composite material. And composite, you may understand, one is the compound, another is the composite. And what is the difference? These two, compound is It's have their own structure. Composite means it is a mixture of more than two materials, and mixture is like that. They are not reacting to each other. Means they are retaining their identities. They are present in the composite with their own phase. Otherwise, if reaction take place, then something new will form and it will be again a new compound. So we are not making a compound, we are making a composite. We are making the mixture of these two, and they are being present in the materials in the different matrices. So for that, this graphitic carbon nitride and this zinc cobalt oxide, these hybrid electrode materials are being fabricated. And then firstly, what we will do, we will make the zinc cobalt oxide by adopting any simple techniques, either sol gel method, co-precipitation, hydrothermal, whatsoever. And then you can make some graphitic carbon nitride, and you mix both of these two and do some heat treatment, all that. And finally, once you prepare this composite, then this composite material has to be spread over this nickel foil, nickel sheet. And then this electrode has to be prepared. And then these electrode has to be tested for the electrochemical reactions. So we see that firstly, naturally, if you make any material, so that must be, you have to check it, either your material is being formed in the pure phase or not. So that can be done through the XRD analysis. This is XRD for ZnCO2, this is graphitic carbon nitride, and this is for the composite. So in composite, we are getting all these peaks corresponding to the ZnCO2 as well as the graphitic carbon nitride as well. Then only you could say it's a composite, because both materials are present with their phases. Otherwise, if you are getting some new peaks, it means something new will form. So that composite has been prepared first, and then you confirm through this XRD analysis. And the second thing is then you have to measure the surface area as well as to the pore size. Surface area you have to be checked, because naturally, as much as the surface area is large for your electrode materials, so their capacitance will be large. Because see, that depend upon A is the area of your electrode. It must be large. Surface area must be large. And that could be checked with this BET measurement techniques. BET measurement techniques is that your material is porous, then some gas amount is being adsorbed. And on the calculation of the amount of these gases, so this pore size and surface area is being calculated. So in this method that we found that the surface area is around 46 meters square per gram, means the 1 gram of material, it could be spread up to the 46 meters square. And the pore size, this is 2 to 50 nanometers. Pore size is also very important in these the energy storage materials, because you know that the electrolyte ions, once they move, they will enter into the pores. So how many ions are entering into the pores, how long they are staying in the pores, that affect the performance of your energy storage device. So for that purpose, we use the pore size is 2 to 50 nanometer. This is called the mesoporous range. There are three things: microporous, mesoporous, and macroporous. So microporous, this is less than to the 2 nanometer, mesoporous 2 to 50 nanometer, macroporous 50 nanometer to above. So the optimized value of the pore size for these materials, this is 2 to 50 nanometer. That it is required that 2 to 50 nanometer it must be the pore size. Region is
साले फुल टॉस बोलती मेरा लंबा नहीं ले रहा लड़के
Sir, you please continue.
okay. So that problems comes in the online.
Yes, actually, some of the participants, they just joined and they are on mute initially. They create problems.
So this is the pore size is important in that sense. If suppose pore size is very small, less than to the 2 nanometer, then the electrolyte ions, they could not enter in the pores in sufficient numbers. And if it is very large, then what happens? They will enter and just immediately comes out. So because of that, discharging time is affected. So we want that this pore size, it should be the very, it should be the in a optimized range. It should be in the optimized range, and this optimized range for the energy storage devices, this is the 2 to 50 nanometer. So this 2 to 50 nanometer is the pore size range that is good for these energy storage devices. Then we see that the CV curve and GCD curves for these energy storage devices, that you could see this is the CV curve. So we can see in the CV curve, so clear peaks you are getting for the oxidation reduction. So immediately you could say it's not a EDLC material. There is no electrostatic charge storage here. This is the charge storage electrochemically, because the oxidation reduction take place, but it is not purely the battery type. How you can identify this? Because peaks are not as sharp as in the batteries. So you could say it's a combined effect. There is a pseudocapacitor. So pseudocapacitor nature is being, you could say, and even this is the GCD curve. It's again showing this kind of the humps. Not, they are not linear as in ADLC. So naturally, it is very clear that this kind of electrode materials, they are not pseudocapacitive. Sorry, they are not electro EDLC. They are the pseudocapacitive in nature. Then their specific capacitance is being calculated. So this is the assembly of the final assembly of the fabrication of supercapacitor device. You can see that. So how this can, firstly, we make these materials separately. They have been coated over there. So these are the real pictures of the fabricated electrodes. So over this sheet, we have been, this 1 centimeter square area is being coated by the materials. So these electrodes are being prepared. And then what we do, because to make the full cell, what you have to do, firstly, on the bottom, it is a nickel foil. Suppose over that, there will be the material, this composite material is being coated. And after that, there is a gel electrolyte. Gel electrolyte, it is a combination of PVA plus KOH. So this gel electrolyte is formed separately. And then we have been coated over this gel electrolyte over the one electrode. And then we will put another second electrode on the top of this. And in that way, so that we can have the contact on both these two sides. So then this final assembly can be prepared. So this is that's how you can prepare the full cell. And one thing is that it is flexible in nature. You can fold it in any shape. So with that, this zinc electrolyte concept, we can make this flexible structure, and that can be done for this gel electrolyte material. So then we have been tested for the full cell. So this is full cell structure. This is the CV curve. This is the GCD curve. Again, indicating the pseudocapacitive nature of the material, that they are pseudocapacitive in nature. And this is then energy density, power density is calculated. So energy density for this device, this is 39 watt-hour per kilogram. So this is very, very good as a point of view of the capacitors. So it is 39 watt-hour per kilogram, and power density is 1478 watt per kilogram. So this is a very good value, and there is a quite significant enhancement in the energy density value by adopting this strategy to make the composite of this graphitic carbon nitride and zinc cobalt oxide. So it is significantly improving the energy density, and the cycling performance is also good. That we have been tested up to the 10,000 number of cycles. So 75% efficiency is retained up to the 10,000 number of cycles. So as compared to the batteries, that is good, because battery generally up to the 2,000 cycles, their performance goes down. But this is up to the 10,000 cycles, they are retaining up to the 75% energy efficiency. So that is also quite good. So only thing is that it is improved quite now up to 39 watt-hour per kilogram. But we have to improve this towards the battery range, at least 150 or 100 watt-hour per kilogram. Then we can think of to replace the batteries with supercapacitors. So you see that for this device, the key feature of this device is basically, it is first thing, it is flexible in nature. You can fold it into the different shapes. Second thing is no separator is required, because gel electrolyte itself working as a separator, because separator are also the polymer materials. So this gel electrolyte is working as a separator also. So separately, you don't need to require to put the separator. So, and energy density, that is quite good. It is 39 watt-hour per kilogram, and power density is already high. This is 1478 watt-hour per kilogram. So that is this is the approach of making such kind of the supercapacitors. They are being used to light up the LEDs to check their practical applications, and they are being made. So now we can see that this is the another work that where we use some other materials by the copper doping. for the solid state symmetric supercapacitors by using this nickel foil, and again this zinc cobalt oxides and nickel foil on this again. So it's a symmetric again using gel electrolytes. So this zinc cobalt copper cobalt oxide gel electrolyte and zinc cobalt copper oxide symmetric supercapacitor is being fabricated, and you could see that it's a the bat measurement. Again, you see that for any the supercapacitor device, you want to check their performance. Naturally, you have to see there how much is pore size, how much is the surface area, what about the CV, and then you can calculate by the CV and GCD you have to check, and then there is some formula you can calculate the capacitance by measuring the area. So capacitance you can calculate, charging discharging times you can calculate, and then you could say that what may be the practical application for that. So this is through the BAT results. We have seen that the pore size, it is 52 meters square per gram, and this is the surface area, and pore size, this is 2.5 nanometers. So again, it is in the mesoporous range. Now this is the CV curve. It's you see that again the peaks are there, oxidation reduction peaks are there. It's indicating the pseudocapacitive nature of the material. It is pseudocapacitive and non-linear as well. So it clarifies it is a pseudocapacitive, and for a single electrode, the capacitance is 1425 farad per gram. That is for a single electrode, not for the device. For device, it will be 1/4. So this is the quite good value of the specific capacitance is observed. And if we see the cycling test, the 95% of the specific capacitance that is retained up to the 2000 number of cycles for these materials. And then you can see the symmetric fabrication of some other device. This is the zinc cobalt copper cobalt oxides. There is again the gel electrolytes. So again with this we have been gone through all these CV measurements, all these specific capacitance potentials, and finally that we have been tested it for this the energy density and power density. The energy density amount for this device is 55 watt hour per kilogram. So this is the improved further, as previously it was 39, but for this composition for this material, this is around 55 watt hour per kilogram with the power density of 2621 watt per kilogram. So that is this is the strategy should be there. We have to make the composites in that way so that their capacitance would be large, and once the capacitance would be large, the energy density will be large because E is equal to half CV square. So C should be large and cell voltage must be large. So for that you may use some specific electrolyte, either they are maybe organic or some gel electrolytes. So then only the energy density will also be that will be good for these devices. So this is the another thing that traditionally we have been designing some asymmetric device. Earlier they were the symmetric. So in asymmetric we have been selected here. One of the electrode is the activated carbon, and second electrode, this is the again metal oxide based material. So that is the asymmetric because both electrode are of different materials, not the same. So because of that it is asymmetric, and then this asymmetric device have been fabricated similarly, and this is the everything that we have to be firstly tested through the XRD. Then these kind of the morphology of the material is this kind of the spherical balls are being formed. So that has been checked, and for this is the elemental analysis for these nanoporous spheres. And then you have to be again and checked this is the BAT measurements we have to be performed, and to similarly see that how much is the pore size, what is the surface area. So by measuring all that, we have found that the surface area is basically the pore size, that surface area is 22 meters square per gram, and this is pore size is 11 nanometer. So again, this is in the mesoporous range for that. So these are the CV curve for that. So here you see already that now we are using activated carbon. So the shape, you can see that there is a dominance of the EDLC behavior in the CV curve. You can notice through that, but still it is not purely EDLC. It is the pseudo-capacitive. So non-linearity is there into the GCD curves, and then you can see that how much is the energy density for this. So energy density is around 115 watt hour per kilogram. So that is very, very good and approachable towards the battery side. So the thing concerned only that we have to improve the energy density for supercapacitors, then they will have the very good future and they will be utilized widely for the energy storage applications if we have this energy density is very, very large for the supercapacitors. So this is the practical demonstration of this assembled asymmetric supercapacitor device. So these are the 7 supercapacitors. They are being adding in series, and then we have been light up this 12-volt LED that is being patterned in forms of the NITK. So with help of these 7 device, we have been light up this LED for this 7 volt. So thing is that you see that what we have discussed in this presentation. First thing we have discussed some about that how you can do the energy conversion. So simply by using the water splitting, we have been fabricated these hydroelectric cells. They could convert water into the energy. Simply you just pour some amount of water and it's a very smaller amount. You can get energy and that could be utilized for lighting purposes. Second thing, we have seen that how we can utilize the agricultural waste materials. So if the farmers burn them openly, so it will pollute the environment, and if they pollute the environment, so a lot of concern are there. There are some adverse effect on the health. So we have to utilize for some product, some wealth product. So that is the job of the scientific community, that if we want that, we have to take up the research problems as per the demand of our society. And then we have seen that how they can be utilized as electrode material in battery supercapacitors. And we have understand about what is difference between battery supercapacitors and how the supercapacitor materials of the different either EDLC type or either this is battery type, they are being used. And this field has a lot of demand in coming times. You know that there are huge demand of battery supercapacitors because the hybrid vehicles, every company now are working on the hybrid vehicles, and you may also see some of the vehicles on the road. They are having the green plate. They are electric vehicles. So electric vehicles, they totally run on the battery and supercapacitors. So there is a good opening for this field. So that is the energy. It's a good sector itself because energy play a very important role for any economy of this country. So that is from my side for this presentation. Now the session is open for the questioning. If you have any question related to this, then we can discuss.
So any relevant question? Anyone? Session is open for questioning. So any specific question is there? Audiences, please.
Anurag sir, good morning.
Hello.
Hello.
Yes, please.
Sir, this is Sudhanshu from the Nanotechnology and IT Kurukshetra, past student.
Okay.
Sir, how are you, sir? Nice talk.
I am fine. Thank you so much.
Sir, actually, I am working on the polymer nanocomposite for supercapacitor application for the electronic domains.
Okay.
Sir, so I have a doubt for the costing, sir. What is the cost minimization techniques for this?
Cost minimization, you see that there are two things. Firstly, you check the performance.
Okay, sir.
Performance is okay. So then it will to think about to reduce the cost. So cost depend on the material which you are using. I don't know which polymer you are using. So generally
PVDF.
PVDF. So it's not very costly. So
okay, sir.
So only so you see that how much is the ratio of the this PVDF and with other material is what for the composite?
That is the barium titanate and TiO2.
So barium titanate and TiO2. Yes, TiO2 is somehow you could say that some, but not very costly. So,
yes, sir.
So I don't think it will have the much cost for.
Okay, sir.
Yes.
Okay,
So
thank you, sir.
Focus on the performance.
Sure, sir.
So then there will be a demand of the work.
Okay, sir. Thank you, sir.
Thank you. Thank you.
Hello.
Yes, continue, please.
Hello.
Yes, yes, you please continue.
Yes, please ask. Yes.
Sir, I'm Dr. Kamlesh from KBPC, Mumbai.
जी 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 जी. Dr. Kamlesh.
Uh, huh. Sir, I have one more question. What is the role of dielectric material in the supercapacitor?
You see that in supercapacitors, basically we don't use the dielectric materials. So in place of the dielectric, we use the electrolyte. So some of the supercapacitors now they are coming, we use the solid state electrolyte. So in that sense, you could say, but then you have to see the material, okay, how much the material, if they are solid state electrolyte, their ions, they could be able to move. So accordingly, we have to select them. So this dielectric material we use only in the conventional supercapacitors, but not in the supercapacitors, because in supercapacitor they are basically electrochemical capacitors. We generally use the electrolytes. But yes, you could say that we can use some materials, solid state materials, that they may have some dielectric property itself. But again, it will be very clear that they will have only the EDLC effect. You can use it, but they will have the EDLC effect. EDLC effect means charge storage will be only electrochemical, not electrochemical. So then what is the problem will be there? Their energy density will be low if you will use the dielectric material in this. So again, the purpose is that we have to improve the energy density. That will not solve. So that is the actual problem with these dielectric materials. Then it will be like a conventional capacitor. So their capacitance will not be very high. I think you may got my point.
Yes. Next question, if anyone. Next question, please.
Hello.
Hello.
Yes, please continue.
My question is, I also work in supercapacitor application. My question
Okay.
is, the gel prepare. When I prepare the gel with KWH and PVA,
Yes.
the longevity of the gel is not too long. So for a certain after a certain time, the gel performance start to decrease. So what is the replacement for this technique, or how can I improve this process?
You see that the gel, first thing is that the ratio of you don't keep the much amount of the PA. There should be the enough the aqueous electrolyte also. Second thing is you do the testing after packaging properly. Otherwise, it will be dried soon and your performance goes down. So once you assemble the device, then you can wrap it properly with paraffin sheet like that for the
Okay.
testing. Then only it will show you the better response.
So I think no more question is there. So with this, I would like to express my sincere gratitude and thanks on behalf of Department of Chemistry, JC Bose University of Science and Technology, and the other collaborators for sharing your valuable time and knowledge with us. So we are again very thankful for letting insights into the future energy sectors. And definitely this talk will be a type of scientific lubricant, I can say. With the help of that, our students might be entering into this sector. So thank you very much, Dr. Gaur. And I think now this session is over.
Thank you, sir.
Dr. Anurag.
Thank you, madam. Thank you so much.
Thank you for sparing your valuable time and for giving this brilliant lecture. And it was a really very interesting and interactive session.
Yes, yes. Thank you, madam. Thank you.
Thank you so much, sir.
Thank you.
Shreya, please continue.
Now, for the second session, I would like to introduce you all to our eminent speaker, Dr. Garima Dwivedi ma'am. Dr. Garima Dwivedi had done MTech in in chemistry, PhD in chemical engineering from IIT Delhi. Her PhD thesis was on dye-sensitized solar cell, and she has 2 patents, research publication, and conferences presentation to her credit. Her area of interest involves solar cells and reactor design. She also has experience in R&D and testing of petroleum, radioactivity, plastic paper, and pulp-related activities. We welcome you, ma'am.
Thank you very much, Shreya. So I would like to welcome you all other listeners, myself, Dr. Garima Dwivedi. And currently I'm working on this petroleum testing and the radioactivity testing. So this is also actually very good field in which we should all enter. Like people are working on this blending of fuels, and they are trying to make this biomass. So I'm working on this part, the testing of the fuels and their efficiency part. And my PhD work was on third generation solar cell, that is dye-sensitized solar cell. So I would like to share like general ideas, because the students are from different background, like from chemistry, from physics. So here I'm not sharing any of my results. I'm just sharing the general knowledge to all the students, so everyone can cover this part. So thank you, Dr. Bindu. Now can I continue?
Please, ma'am.
Okay. So we all, and really that previous talk was from Dr. Anurag was really good. And these two talks are a little bit interconnected with each other. As Dr. Anurag covered the point, the energy storage devices. And I'm covering the part energy like solar cells. So once the solar cells start working, we need energy storage devices. Without that, it's very difficult to go ahead with this solar energy. So I'll briefly, continue with this part. This solar cell, we all know what are solar cells. Like solar cells are simply, we get the solar energy from the sun, and with this help of the solar energy, we convert light to electricity. And these electricity are carried through wires for different applications. And we all know this word photovoltaic cells. So in the Greek language, what do you mean by this?
Ma'am, sorry to interrupt you. May we go full screen?
Okay, sorry. Can you please help me to how I can go it, because
ma'am, press F5. F5.
I'm pressing F5, but it's not giving the full screen.
मैम अगर टॉप पर देखेंगे आप, फोर्थ आइकन लेफ्ट में, फोर्थ आइकन सबसे टॉप पर स्लाइड शो स्टार्ट हो जाएगा.
Yes, F5 is there, but it's not. Yes, not. Thank you.
Yeah.
So we all know the solar cell. Now the photovoltaic cell means, photos means like light, and voltaic means electricity. So we are converting this light to the electricity, and for various applications. If we see the solar cell in a solar spectrum, we see it's a UV range is there, visible range is there, and infrared range is there. So we want our solar cell to cover this maximum range for good efficiency. If we see the solar cell, this solar cell consumes no fuel. And actually, we have to look after this pollution part. No pollution is there. And we can handle wide power handling capacities are there in this solar cell. Like in case we are going for some chemical reactor designing part. So we can now go ahead with the planning that we can design a reactor that they are working with the help of solar energy. We should try to opt for the solar energy in compared to like we are using coal as a fuel in thermal power plant. So now we should start working on this part that we can use the solar energy for this working of this reactors part. So in our remote areas, there is no power cut. Some power, we need a continuous power supply. So we can go ahead with this solar energy for this power supply, and it is free, it is limitless, and it is environmental friendly. So if we see the history of solar cell, so first this photovoltaic effect was observed by Becquerel in the year 1839. And the first solar cell, silicon working solar cell with the efficiency of just 1% was patented by Charles Fritz. And the first working solar cell with a reasonable efficiency of 4% was invented by Bell Labs. So if we see the solar cell which we are using, like they are having efficiency of approx 26%. And in the commercial scale, we are having efficiency on 18%. So now people are working to improve the life of the solar cell, to improve the efficiency of the solar cell. So this is the like first solar cell in the year, which was like by Bell Laboratories. So I just want to share this screen, this paper, very first paper on this solar cell. And if we see the solar cell technology, either we can use the solar cell for direct heating, like that is known as passive part. And in case we want to use our solar cell for this active part, like in case we are getting the solar energy, so we take the solar panels. With the help of solar panels, we are using for this generating electricity. And this electricity is carrying through wires for different application in our home, in our industry, wherever our requirement is there. But in the passive part, like, we are using this solar energy directly for the heating purpose or some other application. So people are really focusing on this active part of this solar cell. So people are working on this solar cell technology. People are working on the solar cell, different types of solar cells. And to further increase the efficiency of the solar cell, people are using the design of the solar cell. Now, how can we design so maximum efficiency we can get from the solar energy? So if we see basically the solar cell are divided into 3 generations. Like normally the solar panels which we see in our like rooftops, these are like first generation solar cell, silicon based solar cell. So the advantage of this part is that this first generation solar cell is that we are getting a good efficiency, and cost is like little bit costly. Now, if we go for the second generation solar cell, but the commercially available solar cell are like first generation solar cell only. And if we seek the second generation solar cell, the second generation solar cell, what the people are working on, we decrease the amount of material. These are like we call thin film solar cell. So in this, the amount of material which we are using for the solar cell are less as compared to the first generation solar cell. So, but the efficiency of this solar cell is like, we can see that comparable to silicon solar cell, but they are little bit less costly, but they are not that much commercially available, because some of the issues are there, and then some of the environmental issues are also there with the second generation solar cell. So now the latest, the people are working on this third generation solar cell. So in the advantage of this third generation solar cell is like the efficiency of this solar cell are 30% as compared to the first generation solar cell. But they are still on the like lab scale only. Commercially, some of the companies are working, and but still not up to the mark for this commercial availability of this third generation solar cell. So in my presentation, I'll broadly cover this third generation solar cell. In the third generation solar cell, I'll cover this DSSC part. So what all parameters are there in this solar cell? What all components are there in this solar cell? And as maximum students are in this group. So I want on what all part you can focus as a chemistry background people, as a like material science background people. So we can go for the enhancement of the efficiency as well as the stability of this solar cell. So now let me continue with this DSSC part. This is third generation cell. If we see in the third generation, we have this DSSC, quantum dots, or we have an organic solar cell. But in our part, I will broadly convert this DSSC. So if you see the DSSC, it was like introduced in 1960s. And in 1988, the first solar cell was invented by this grid cell group. And in 1991, very first efficient DSSC with the efficiency of 7.1 was developed by EPFL Switzerland. So these are like the now so many labs are working on this DSSC part, and in India also many people are working on this DSSC part. So and G24I is the first company to commercialize this DSSC technology. So if you see the DSSC, it consists of it's a like sandwich type assembly. There is one working electrode is there. There is one counter electrode, and between those electrode, electrolyte is there. So it's a like sandwich type assembly. On the working electrode part, if you see, this is like photoanode. So in photoanode, we need high surface area. So why we use nanoparticles? Nanoparticles are like very small in size. Surface area will be there. The more dye can absorb, anything can be absorbed on the more surface area. So if we see the photoanode part, on the photoanode, this is a conducting glass. So in this conducting glass, a layer of TiO2 layer is deposited. We just make some paste. So this part will provide a more surface area for the dye absorption. And the second one layer is like TiO2 nanoparticle of size 400, approx 400 nanometers. So these are like little bit bigger in size, but these particles will help in the scattering of the light, because we want once a light enters, it should scatter. And on this particle, because we want the visible range of light particles should be absorbed, so we just absorb the light which will cover the maximum visible range on this particle. So for in our case, we are using this like ruthenium dyes. If we see counter electrode, so and this is also conducting glass. These both are glass. On this conducting glass, we deposit a layer of platinum, which will work as a catalyst. And in between these two electrodes, we insert the electrolyte. So now how the working of this third generation solar cell, that is DSSC, will work. So if we see this conducting glass is there, the conducting normal glass on which there is conducting coating, that is like FTO, that is fluorine doped tin oxide. Commercially, two types of conducting glass are available. Either we can use FTO or ITO, but we cannot use ITO in our DSSC because we have to sinter this. Security will come as an issue, so we'll preferably we use FTO in our case. And we deposit the layer of TiO2 nanoparticle. We just make the paste formulation and we deposit this TiO2 nanoparticle, on the top of which we deposit a layer of 400 nanometer particle, that is of same semiconductor nanoparticle. And once we dip this electrode in the dye for 24 hours, and you can see these particles are very small in size, so maximum dye is absorbed on these particles. And these particles are little bit bigger in size, so very less dye is absorbed on this particle. In case you can see on the glass slide also. This is a counter electrode. We deposit a layer of platinum on this FTO glass, and at the end we just insert the electrolyte and we just seal this cell. So this is like a sandwich type assembly. Now we can see the like dimension of this. The size of the dimension of this TiO2 nanoparticles is like 6 to 8 micrometers. And if we see this, like this is like 5 to 10 micrometers. It depends on what technique, or like we are having some automatic machine for that, or we are using like handmade techniques. So more or less the dimension is like this only. And this area is filled with electrolyte. So this complete part is known as working electrode. This is like counter electrode, and in between this electrolyte. So now how this solar falls on this solar cell, that is like sandwich type assembly solar cell, the photons, this dye is working as absorbing the photons. So when the dye gets the photons, the dye goes to the excited state. Once the dye goes to the excited state, it will transfer electrons to this TiO2 nanoparticle. Now, once the dye transfer electrons to the TiO2 nanoparticle, dye become oxidized. So we want the solar cell should keep on working. So what will happen? The dye needs
Dr. Garima has disconnected somehow, I think. She's trying to reconnect. Please wait. Yes, Dr. Garima has joined us. Welcome.
Am I audible?
Yes, ma'am, you are audible.
Hello?
Yes, ma'am, you are audible.
Okay. Okay, thank Sorry for the interruption. It happens with this online. Uh, I'll start with this working principle of this DSSC. So basically the DSSC, basically the DSSC consists of two electrodes, that is working electrode as well as this counter electrode. So on this working electrode, as I previously explained in my slide, there is a layer of TiO2 nanoparticles, and this on the top of this we absorb the dye. So dye transfer electrons to the TiO2 nanoparticles. Now this oxidized dye needs to be regenerated with the help of this redox couple, and this electron travels to the outer circuit to the counter electrode, where it will get regenerated again. So this process will go on, this cycle process will go on, will get the load, and the DSSC will keep on working. So as we have seen the structure of DSSC, it's like working electrode on which we deposit make it conducting glass by depositing the layer of fluorine doped tin oxide, on the top of which we deposit the layer of TiO2 nanoparticles. We just make the paste of TiO2 nanoparticles of size 21 nanometers, and we deposit on the top of this working electrode. And the top of which we deposit the layer of 400 nanometers and this is like counter electrode, which is also a conducting glass, on which we deposit the platinum, and in between these two cells we inject the electrolyte. So if we see any solar cell, so how we'll get the efficiency of the solar cell? So for this efficiency of the solar cell, we want, this is the IV curve for this solar cell. So we want our solar cell should give maximum current, maximum voltage, and with minimum resistance in our solar cell to get the maximum efficiency of the solar cell. So if we see the fill factor, value fill factor varies from 0 to 1. So we want this value should be more and more towards 1. And the value is more and more towards 1, so we'll get the squareness of this curve. And this is like IV plot, in which the maximum voltage we want in our solar cell is this. And this is the like maximum current which we want in our solar cell. So we want our solar cell should give maximum efficiency. So voltage factors are there of and it's slightly inclined. So how to get the and the wavelength, the color of the light. If you see the fabrication of DSSC, it's quite easy. We just take the conducting glass, as we all can, initially we can fabricate this solar cell. So we take this conducting glass, on we deposit this TiO2 paste formulation, specific method we have to use to make this paste formulation. So we just deposit the TiO2 paste on this slide. And we just dip this electrode in the dye, whichever dye we were using in our system. So on this electrode, we deposit we select. So what's the advantage of this DSS is like, we can use different dyes in our solar cell. People are working on this natural dyes, the natural dyes which we can synthesize from our fruits and vegetables also. So in place of this dye, you can use any dye like from any of your fruit, any like from beetroot, from like from green vegetables, you can get some dye. At least you will get something working. Like you can see that solar cell is working. It's like very initial part, which everyone can do this. And we can see the of the device. So we can cell is like, these are like transparent. So you can use these solar cell in our window panels also. So you can just get a look also, as well as you can use and people are working on the replacement of this glass with some flexible material. So now the solar cell are like flexible in nature. Once the solar cell are like flexible in nature, so you can use this solar cell in like in your clothes, in your bags. So you can just use this pack bags, and on the backpacks you can use this flexible substrate. So you can just mount this solar cell on the bag. So that solar cell will work as a charging port for your laptop, for a charging port for your mobile. So it can have a wide application of this solar cell. And one really very good advantage with this solar cell is that it can work, the working hours for this solar cell is quite long, because these solar cell work comparatively good in morning and the evening hours. So, and as second is like the working, although efficiency is quite low as compared to first generation solar cell, but if you see the working hours are quite long as compared to first generation solar cell. And if we to start with this, to get into this solar cell, to fabricate this solar cell is like quite easy. And there are so many parameters on which we can work as a chemistry background people, as a physics background people on this solar cell. So as maximum students are there in this group, so I wanted what on parameters you can play with this solar cell to get efficient solar cell. And it's like for this working electrode, we are using simply FTO glass, that is like conducting glass, on which we deposit the TiO2 layer and we absorb this TiO2 into dye. Now, what parameters you can touch with? Like this FTO glass. So you can work with some flexible material. You can try to replace this FTO glass with some flexible material. And second thing is like we are using TiO2 nanoparticle. So you can on different types of nanoparticles, like you can go for some other semiconductor nanoparticles also. And even you can work with different structures. Like you can, in place of this nanoparticle, you can think of using nanorods. People are working, so many literature is there, but you can think of using, and in case some more ideas, like in case of nanoparticle, you can insert the nanoparticles inside this nanorod, or the nanorod is doped with nanoparticle. So as a like material science student, chemistry background student, people can really work on different nanostructures to get more efficient DSSC. And like dye. So the students who are from chemistry background can really work on this dye part. So dye part is like, dye part should be like that. It should cover the maximum spectrum. So people are like working blending of 2-3 dyes for this DSSC application, or they are working on different structures of the dye that but there some requirement is there that dye should get attached to the TiO2 nanoparticle. Some bonding should be there, and you can work on different students from the chemistry background can get into this to get the dye of maximum absorption spectrum. Now the thing is that like electrolyte, I'll share some of the like scope for this. Like in this electrolyte part, if material what on students can really work sorry for the impression. I don't know what's the problem with this internet. So if you see, as compared to the silicon based solar cell, DSSC are like of very low cost, and like it's very easily to fabricate this solar cell. Moreover, the DSSC shows the higher conversion efficiency as compared to this silicon solar cell. Like in case we are having some cloudy days, condition DSSC works much better than silicon solar cell. So these are like some of the advantage of the DSSC. And if you see this configuration for this DSSC is like bifacial. So it can work from both sides. Is quite long. like in the work hours are quite long as compared to the
अरे मैं शीतल शीतल
but there's like some of the limitation of this solar cell, and we really want the students and the fresh minds should involve on this part to get more efficient DSSC. Like the stability is the main issue for the DSSC. The electrolyte which we are using in our DSSC is like after some time it just dried off. So once the no electrolyte is there in the DSSC won't work. So we want that people should work on the more on the chemistry, mainly the students from the chemistry background should come up with this electrolyte part. So people are really working on this replacement of this liquid electrolyte with some gel electrolyte and like solid electrolytes. So to get the more stable DSSC. State only. Efficiency of DSSC is quite low. Like dye needs to be regenerated to light, but sometimes what happens? The dye used to get regenerate the electrons from the TiO2 layer only. Like these all parameters makes the less efficient DSSC. And the different types of substrate with the on which we can fabricate the this DSSC and the electrolyte part. So if we see the research scope in this in our like in a solar cell, so we can think of exploring dyes, we can think of exploring the electrolyte, although a lot more literature is reported for this DS in which people are using natural dyes from like all the fruits, from all the vegetables, from mixture of dyes, what all efficiency you are getting with the DSSC. People are working on different nanostructures like important thing is like in the counter electrode, we are using platinum as a, we are just using platinum sol as in on this counter electrode for the regeneration of the electrolyte. So like people are working on the replacement of this platinum with some low cost material, like some carbon based material. People are working on this replacement of platinum with this carbon based material because which so you can work for this we can work with the dye part. So we can just work on the blending of the dyes. So we can think of using quasi-solid DSSC and solid DSSC. Quasi-solid means we are replacing dye electrolyte with the help of some gels, some solid polymeric materials. And we can think of using eco-friendly material in a DSSC. So once a solar cell is not in use, so if we just discarded solar cell, it should not get any environmental impacts. So we should try to think of using eco-friendly material in our solar cell. And the students who are really interested in this mathematical part, so they can just at every interface of this DSSC, there should be some proper mathematical modeling to get the deeper study of this DSSC. Like normally we just we just do the electrochemical study for this DSSC, but we want the people from like maths background should come ahead to get into the DSSC part. As we can say, on the basis of like theoretical calculation, the efficiency of DSSC is like 20 to 25%. So we want that people from different backgrounds can join this DSSC part to make the DSSC more stable, more efficient, and better understanding of this DSSC. So like that's all about my presentation. So I want that this session should be like very interactive. I want all the students can come up with more ideas for this DSSC part.
Hello. Students, yes. The students, the session is open for questioning and answering. So the questions are welcomed from the participants. Ritika want to ask a question. Ritika, please ask.
Yes, Ritika.
Good morning. Good afternoon, ma'am.
Good afternoon.
Ma'am, in conventional methods, like you said that silicon cell method, so we used silver paste that very costly in conventional methods. But in a DSSC, do we need a silver paste to join like in large scale?
Context. Basically, at the end of this lecture, we need to make contacts. So we just to make the contact, we need a silver. Any questions from the audience? This is like in case anyone is interested in this research part. So I just don't want to share my results. I want, in case you people are interested in this part, so I want you just raise a question. What all background I do have, I can just give you some ideas. So you can go ahead with this research part.
Any further questions from participants?
In case you want to just ask a basic question, because this presentation is like very basic, very basic. So any student from any background can get some idea of the DSSC. So just you can ask any silly, any basic question also.
Ma'am, the presentation is very basic, but at the same time, this is very important also. The topic is very, very important in the current scenario.
Yeah.
So participants, this topic is very important, and if you have any question, you please ask.
So at the end, I just want to share one thing also. In case some of the students are here and they really want to enter in this PhD program, or they are interested in the research part. So currently I'm working on the plant design part. So as you have all seen this parali burning and this farm fires, na? So my research interest is also in this plant design part. So in case anyone is interested to convert this like rice straw, and the basically the people from the Delhi NCR background have seen this news, pollution and all what all things are there. So
Yeah.
I wanted people should come up with some good ideas how we can reuse this rice straw to make a fuel, biofuel. That is also like very interesting topic. And how you can, in case some are having some interest in like plant design part, so you can think how you can make the setup to use this rice straw to make the biofuel. So you can replace the coal which we are using like in thermal power plants with the help of this biofuel. and you will sort out this problem of farm fires and pollution and what all things are going on. And
Your voice is breaking, I think.
bio topics are like student from any. Am I audible or still?
Yes, ma'am. Now it's audible.
So in case students are not asking question, but I just want to share some of my ideas on which student can really work. And like hydrogen storage, very important topic. Energy, solar cell, energy storage, hydrogen storage, and this biofuel. These are like very good topics and government is funding a lot. So I want you students should start making project proposal also. This is like out of the presentation thing, but I just want to share with you all, and you can start making some project like some funding from the government, and you can start working on these topics. So in case someone want any help from my side, like from mathematical part or from like plant design part, I am ready to help you all. You can just get my mail ID from your faculty members.
Sure, ma'am. Thank you, ma'am. Thank you. So, participants, any other question? Is there any question? No? Okay. Ma'am, thank you so much, Grima ma'am, for this nice talk. The talk was very simple. I think every student, even all the participants must have understood the concept and must be benefited of this. And why the topic is important, even I can see whenever I visit my native village. Nowadays, I can see out of if there are 10 fields, 10 farms, so out of those 10, 2 and 3 farms must be they are having solar panels for the generation of electricity. So I think this trend is now going on, and they are using that electricity for any means their other tasks. So that's why the topic is important. The solar cells are being used at commercial level these days. So thank you, ma'am, for talking on such an important topic, and thank you for accepting our invitation to talk here, sharing your ideas. Thanks, ma'am.
Thank you.
Now, participants, we will have a break, and we will meet again at sharp 2 p.m. for our last session of this 4th day of our this 1 week short-term course. So join timely, sharp at 2 p.m. And Bindu ma'am, is there any other special instruction?
No, sir. Thank you so much. Thank you, Dr. Garima. Thank you. It was really a lovely talk. Although some technical issues was there,
Yes,
but
I'm sorry for that.
No problem, ma'am. Overall, it was a lovely talk and quite interesting and interactive. And participants had some queries also. So I'm quite delighted that after all, it went well.
Yeah.
After all these technical issues. Yeah. Thank you so much, ma'am. Thank you very much.
Okay.
Thank you.
Thank you, ma'am. Thank you.